All right. Welcome everybody to our webinar. I'm especially excited about this one for three particular reasons. The first one is that it's a very cool application, as you'll hear about, therapeutics for ADHD kids, the digital therapeutics. But also it's using the latest and greatest research from cognitive neuroscience, which is a very interesting domain in it of itself. In fact, so interesting that I did my PhD in it. And thirdly, also just from a quantitative perspective, the tools that are being used and the technologies invented by Alex that he's going to talk about are just really, really cool, combining the best of Bayesian modeling and neural networks and how you can basically have likelihood-free inference on all kinds of models like cognitive neuroscience models, as we'll be showing here. I'm Thomas Wiecki. I'm the founder and CEO of PyMC Labs, our Bayesian consultancy. And this is a project that was part of our engagement here. And just following on with introductions, I'm passing it over to Alex Fengler.
Hey, I'm Alex. I just finished my PhD in cognitive science at Brown University in the Frank Lab. Some of the work we are going to present here is from that time. And I'm with PyMC Lab since roughly 1.5 years now, mostly focused on the efforts with Akili.
Great, thank you. And next up is Titi.
Hi, I'm Titi Alailima. I've been with Akili for about 7 years. I've been a fan of PyMC for something on the order of 10 years. And we happened upon Thomas's PhD research and thought, hey, this is a guy we want to talk to. And I approached him after a meeting and started talking about leveraging some of his expertise, and then he found other people with similar expertise to get us going.
Very cool. Yeah, that was a great, well, not coincidence. Great happened. And then we have Andy, who also was integral to this project, and he's also then gonna launch into the first part of the presentation. Then we'll have a bit of a discussion and a Q&A period afterwards. So yeah, Andy, take it away.
Awesome. Thanks, Thomas. Hello, everybody. I'm Andy Heusser. I'm a senior data science manager at Akili. I've been with Akili for about 4.5 years. And prior to Akili, I was a postdoc at Dartmouth College with Dr. Jeremy Manning, designing algorithms to help people learn as efficiently as possible and other computational approaches to modeling human learning and memory. And prior to that, I was a grad student at NYU with Dr. Leila Debachi, studying fundamentals of human learning and memory and cognitive science more generally. Yeah, so Alex, if you wouldn't mind sharing your screen, we can go right into a little background on Akili, for those of you who are not familiar with the company.
Is this good?
Perfect. Yeah. So at Akili, our mission has been really to develop medicine that is delivered through captivating digital experiences. So put another way, we make video games that are designed to both measure and improve cognitive function. Next slide, Alex.
Yep.
So we've been at this for quite a while now. Titi's been here for most of the time this company has been around. So our approach is really, and what kind of differentiates us from other, I think, brain training products is that we're grounded in rigorous clinical research. We've got over 20 clinical studies across lots of different disease populations and thousands of patients. And one of the more important milestones for the company recently was that in 2020 we received FDA authorization for our first product, which is called EndeavorRx. Next slide, Alex. So EndeavorRx is a video game. It was designed, or it's been demonstrated to improve attention in kids with ADHD, and specifically labeled to help 8 to 12-year-old kids with inattentive or combined type ADHD. The basic idea is that you play this game, you have a character that's going through this ever-changing course while capturing creatures and avoiding obstacles. And there's dozens of worlds that you explore along the way, as well as lots and lots of rewards to really keep people engaged with the treatment. And so we're just going to show a little video that kind of highlights what the game looks like, so you can get a sense. Yeah, no, go ahead, Alex.
Imagine a medicine made up of pixels and play. Created with cognitive science and proven in clinical studies. A video game that's FDA approved.
That's what I'm talking about. Woohoo!
That invites your child to discover new worlds.
You did it! Nice!
Build their universe.
That question was tough.
Capture mystic creatures. Boost past challenges. And unlock new characters.
Oh yeah!
All to create positive change. Introducing EndeavorRx, the first prescription ADHD therapy
Look at us, rocking it again!
delivered through a video game experience. Designed to work alongside your treatment plan.
Hey, whoa! You were all round, and I was all woot! Awesome!
And proven to improve attention.
All right, cool. So before I hand it over to Alex to walk through the work we did together, you might be wondering why we actually teamed up with PyMC Labs, and we'll talk about that a little bit later. But so in our clinical trials, we have observed these improvements in attention function at the population level, and after typically a month of treatment. And the way we've done it historically, for example, in our STARS pivotal study, is that participants take a battery of cognitive tests before the treatment, and then they engage with the game over the course of a month, and then they come back and they do another round of cognitive assessments, and we can measure before and after to see whether there are notable improvements in cognitive function. That's all fine, that's great, but we really think we can do even better than that, because we have a digital therapeutic product with rich gameplay data that's collected every time that the patient interacts with the device. We have this massive opportunity to better understand the time course of improvement, who is benefiting the most and why. So we've tapped our brilliant friends over at PyMC Labs to help us crack this tough nut, because they have deep expertise in building these cognitive models and in Bayesian modeling more generally. So with that, I'll hand it over to Alex to walk through the work that he mostly led under Thomas's advisement in collaboration with our team. Oh, and we should be sure not to leave Ricardo out as well. Ricardo played a huge role.
Yep. Okay, I consider this handed over?
Yes.
It has been handed. The torch has been handed.
All right. So the title of this part is going to be Likelihood Approximation Networks in PyMC. So what that title is about is going to become clear sooner or later during the presentation. But let's start as a starting point. So let's just unpack a simplified version of this EndeavorRx game. So consider this other game, right? It's somehow in close analogy. It's called NeuroRacer. It's attached to a Nature paper in 2013. So in NeuroRacer, if we are playing this game, we'll drive around the circuit here using our controls. And on the circuit, are going to appear some road signs. These road signs, there can be several of those. However, only one of the road signs in a given, let's say, condition or level, only one of those road signs is going to be good. The rest of the road signs is going to be bad for us. So we consider the good one the target. The rest we consider no targets. In this case, we are looking at a target. So we should correspondingly then press a button on our controls. If we see a target, we press a button. If a road sign appears that is not a target, okay, this should have been down, but okay, we get the idea, then we don't press that respective button. Okay, now we just repeat that over a bunch of trials or levels. And that leaves us with 4 types of responses here. So good symbol, we press, we consider that a correct go decision. Good symbol, we don't press, we consider that a false no-go. If it's a bad symbol and we press, it's a false go. And if it's a bad symbol and we don't press, then it's a correct no-go. Now we notice just one thing about this. If we or the player presses, then we'll actually observe that as a reaction time. If the player doesn't press, then we observe only a choice. I'll return to that idea a bit later, but that's just to prime that. Okay, so now, since we talked about go and no-go choices, in cognitive science, this is also, you could consider this task as an example of a go, no-go task under extra load that is coming from navigating the circuit, for example. So one paradigm to model go, no-go tasks is based on so-called, what is our model here? So-called drift diffusion models. Okay, so what are these models about? So these red moving particles here, they are essentially considered a state of evidence, an instantaneous state of evidence towards one or the other choice, right? So this particle is going to move around, and at some point it's going to hit one of these bounds, either the upper or the lower bound, and we consider that then either we decided not to go, so we won't press, or we decided to go, so we'll press. The histograms on the top and bottom now represent the choice and reaction time distributions respectively for these choices. All right. So all is well, we can now use that model. That model is going to have a bunch of parameters, and we plug that in as a likelihood into our base rule. That's a rule that I hope everyone in this webinar is fond of. And we could then proceed with inference. So let's just take one step back. Parameters, okay, I mentioned parameters. What would be the parameters here? So we have a bunch of them here. So one is the starting point of this particle. So that represents some sort of bias. If I start lower to one or the other boundaries, I'll bias my decision. Then I have the drift, which is a fixed perturbation. Essentially, that is considered to come from an evidence signal, a fixed evidence signal that we are collecting over time. And we have a boundary separation here. So the further out, it's basically just moving the bound, which has something to do with how much evidence we need to take a decision. And a non-decision time, which is not something we'll focus on here, but it essentially captures all kinds of processes that have nothing to do with the actual task until the subject is actually engaged, or the player in this case, rather.
Just one point to make it extra clear that this is basically one idea of what cognitive scientists think is going on in the brain of the subject playing the game. And there are models at all kinds of levels. So here we're not considering what is actually happening in the neurons, but we think, well, from a high level perspective, we can describe this with this process of this particle moving around. And actually, this model has been validated in all kinds of different ways and turns out to be, yes, supported by many different directions. And this is useful in, as a cognitive science approach because it allows us to really quantify these processes and better understand what is going on rather than just looking at the accuracy of something.
Okay, yeah, thank you. Okay, so there are two important aspects of this model now that we'll focus on a bit. So one is that the parameters are actually interpretable, and that harks back to what Thomas was just saying. One of the benefits of this model is that from a cognitive science perspective, all these parameters actually mean something to us from the perspective of a cognitive process, parts of a cognitive process. Okay, and the second part is that this is a special case of a whole class of related models, and we're going to go into that a bit later. Okay, so let's just consider what it would mean that these parameters are interpretable. Well, let's just take this drift parameter as an example. So the drift parameter here has something to do with the speed of processing. So for example, maybe if you keep doing this task again and again, you might get better over time, right? And the V parameter sort of is one way of capturing that, where your fixed evidence perturbation over time is going to grow stronger and stronger with each trial, let's say, and that leads you to take faster but also more accurate decisions. Next, we can consider, for example, the A parameter, which was we call it the criterion parameter, the separation of the boundaries. That's a parameter that you can consider as somehow in this player's control. By increasing the evidence threshold, you choose to collect a lot of evidence before committing to a choice, but you'll make less mistakes, but you'll have longer reaction times. If you bring these bounds closer together, you'll make more mistakes, but have shorter reaction times. So this is something that you can consider as a parameter that is really under control, that yet you have under control as playing the game, while playing the game. Okay, so this, as Thomas also mentioned, is, yeah, go ahead.
Yeah, just to add one thing also, which I found super striking when learning about this model is that just by following the simple process many times and then doing histogram over that, which is what you see at the top and the bottom of that, that you get something that really looks like reaction time distributions. Like if humans do this and you do a histogram over the times it took them to press a button, that has this like peak distribution that peaks very quickly and then has this long tail. And yeah, if you follow this process, you get something that looks almost identical, which is kind of cool, right? So you just have this very simple drift process, and then that looks exactly like the end result of what humans are doing. So it's nice evidence, basically, that these things actually do have some correspondence.
Yep. Okay, so I mean, at the risk of repeating a bit, so this has been a very successful modeling paradigm in the cognitive sciences. It has like thousands of publications attached to it at this point across actually many different experiment modalities. But also it does not capture all aspects of the task that we are interested in. So we'll get back to that. So let's first mention this. So the model is actually a special case of a whole class of related models. So maybe there are variations of this model that would be a bit more elaborate while still maintaining interpretability. And those might actually capture certain aspects of our task better. Okay, so now what is this aspect of our task that we might not capture very well? So for the NeuroRacer task, there is a deadline that is attached to a response. So for example, just trivially, if the road sign already disappears from the screen, we might consider like the window for a response to have passed, right? So a player might want to enforce a choice by compromising accuracy towards the end of the acceptable reaction time window. So when you see like, okay, I mean, I know that the window is closing here, so maybe I should commit to a choice, even though it's rather a risky choice, right? So the current model that we have shown here is a model that actually implies a constant evidence threshold. So there would be, you don't have room for such level of modulation in that model. However, quite simply, one could create variations of these models where the bounds, so the evidence threshold, actually comes in over time. And that would sort of reflect a deadline encroaching upon us so that we are going to force a decision at some point in time. So these models might actually be better suited to model some aspects of our game here. Okay, so we would want to do inference with these model variants, but turns out there's actually a fundamental problem. So the derivation of closed form likelihoods is a lot harder for these. And without likelihoods, there's no base rule, right? So that's a problem for inference now. But it turns out that simulation of these models is just equivalently easy across all of them. Okay, so now inference from access to simulators might ring a bell for some people here. So that's you might think of approximate Bayesian computation, or these days simulation-based inference is like a creep of acronyms that sort of transitioned. And that's actually a field with a long history, and there are many recent advances to that. So I just linked a couple things here. So some paper on traditional ABC, overview of modern approaches, and then also the paper that is going to be our approach for the purposes of this work here. So we'll use one such recent techniques that is based on neural networks, and the PyMC workflow that we are building is actually allows us actually to also substitute other techniques in later. Okay, so how would we approach this now? First, we would run simulations. As we said, that's simple to do for all of these models. That might be costly, but it's costly once. Now we'll use those simulations to train a neural network to represent approximate likelihoods. And then afterwards, we just plug that neural network in as a likelihood function, which we can then reuse for inference. And the computation of such a likelihood, once we have the network, is in fact cheap. So inference becomes tractable, and we can reuse the same, we then call it an amortized cost, for multiple different inference scenarios going forward. Okay, so let me just mention that this is part of my PhD work here. So this has been also conducted. So this general framework here. The work for this has been conducted at Brown University in the Frank Lab in the CLIPS department. And let me just go a bit deeper into how the training for this actually works in case anyone cares about that. So what you would do is sample parameters, let's say from a hypercube, sample parameters, that's not a problem. Then correspondingly, once you have parameters, you generate samples from these models and generate data sets. So you have parameters and data sets. From the data sets, you can then go and construct empirical histograms. So empirical response, reaction time and choice distributions. You can construct them. You can also evaluate them. And what you would do then is you take these empirically constructed histograms, turn them into labels for a neural net, so output, and reuse the data points again as reaction times and choices as one feature, or two features if you think about it this way. And the parameters come in as extra features to the neural net. And finally, this neural net, after training, will act as a functioning likelihood function for you. Okay, so this has also been previously made available through a separate toolbox, which really is another brainchild of the PyMC Labs founder, Thomas Wiecki here. It's called HDDM. And so far, so good. But it turns out that in our joint work with Akili, we ran into the limitations of this toolbox. So it relies on an outdated backend, which really compromises forward compatibility and performance. So if anyone wants to know more about that, maybe ask later. But we figured that to break those roadblocks that really come from an outdated backend, relying on a new version of PyMC as the new backend will really sort of allow us to break through all that. So this is now basically the current work. So what are like basic properties of a neural network that we are inheriting here using this kind of approach? So number one is it's differentiable with respect to inputs. So specifically, it's also going to be differentiable with respect to model parameters when we fix the data. And the evaluation speed is helped by the potential for batch processing, which is also something standard in neural network land. Now, let me just mention that previously one of the big roadblocks was that we were not really able to properly use these gradients for sampling, especially not in an efficient manner using the old toolbox. So now, now making use of the new stack here that sort of enables PyMC, we can encapsulate these networks in either PyTensor or JAX, and then supply these networks, either a PyTensor or JAX network, and directly incorporate them into model formulations in PyMC. And therefore, we are able, since these networks are actually differentiable, we are able to apply Hamiltonian Monte Carlo here. That's, I mean, just to say, for people who are not that familiar, that's sort of the main workhorse sampler in PyMC, and actually most of the modern probabilistic programming toolboxes. Okay, so let's look at all this through the PyMC lens a little bit. So how would that look like? So taking our model here as a graphical model, as we would, as we can spit it out easily in PyMC. So we'll see that. So we have 3 parameters here. We ignore for the purposes of our work, the starting point bias parameter is actually not of great interest. So we are not in fact fitting that. So we just have a V, A, and T parameter. So the drift, boundary separation, and T here is for NDT, non-decision time. So those parameters now go into 3 potentials. So what are those 3 potentials about? So I had mentioned that if you don't press, these are unobserved choices. You can have an unobserved, so a no-go choice in a no-go condition, so a bad road sign, or you can have an unobserved choice, so a no-go choice in a condition where, in fact, you should have pressed, so that would be a mistake, right? So those are 2 separate, those are going to be separated out here, 2 potentials, the don't press potentials, and then we have our observed reaction times, and those are basically the ones where the player pressed the button. Okay, so now maybe you don't have to repeat that, but you can match those. You can actually match those potentials now onto the kinds of choices we had mentioned before. And what do we finally do? So now, turns out we are not only using one neural network, we are using two types of neural networks here. So one neural network is here for the observed choices, so the likelihoods, likelihoods that concern pairs of choice and reaction time. So those are here, they are represented as the negative and positive axis, which would be up and down choice. That's just an example. So the blue one is the neural network output, whereas the orange one would be simulations from a given set of parameters, just to illustrate that these networks actually work well. And on the left side, we are using choice probability networks. So these networks are actually trained to just, so in case you have an unobserved choice, the only thing you know is that the player chose down, let's say, chose no-go, right? But you don't know, you don't have any time point for that decision. So what you would do is you would want to have just the probability of not having chosen, which will be the integral over this histogram. So we train the left neural network just on those integrals. And again, if we use model simulations in orange here and the network in blue, we see that these networks also very successfully capture the behavior of these choice probabilities in response of varying, in this case, the drift parameter. Okay, so maybe we can also look a bit at code. So how would we build a PyMC model now to facilitate all that? So you start with specifying priors as per usual. Then there would be some data prep here, but we can skip the details of that. That's essentially just prepping the data to be good inputs to the neural network part. And then here is the neural network part exposed in some detail. So we have the LAN, which would be the likelihood approximation for observed choices, and CPN for choice probability network. That's just for unobserved choices, as explained. So we have the forward pass through both of these. And here, so okay, I say here, I hope everyone sees my mouse. So you have the three potentials appearing that correspond to the, okay, I made a mistake here, I apologize for that. So this potential here, observed RTs, would actually go into the observed RTs potential. And then here you have the unobserved go, unobserved no go. And these potentials refer to those nodes in the graphical model. And that's it. So you have a bunch of, in total here, I kept the line count. In total, this model can be specified in less than 50 lines of code. And of course, one can also refactor this and then just take the whole forward pass out of the actual model specification and just call that as a function. Okay, so then maybe some proof of concept. So for parameter recovery, we tested this. This works very well, actually. This is just a representative example. The graph is powered by our beloved Arbis toolbox. And it works well on really the current set of all of the test cases. And secondly, and that's very importantly now, we checked whether we can actually materialize proper speedups. And so here in blue, so what do we use to check for these speedups? We check the effective sample size, so the number of equivalent independent samples that the sampler generates per second. And here we compare a bunch of methods, but the focus should be on the blue one, which is the old software stack, where we also try to use LANs for the same purpose. And now the new software stack that uses new PyMC with a JAX sampler. And this approach is shows us at least a 10x speed improvement. Okay, that's already the end, actually. Much more in time than I would have anticipated. Check out the newsletter, the PyMC newsletter, if you care. And I guess I hand it back to Thomas.
Great. Yeah, thank you so much. That was really interesting. I do have a couple of questions. So one is, the way this works is we have the drift diffusion model in this case that we can't formulate a likelihood function for, but we can simulate it from it. So we simulate a lot of trials for a certain parameter setting and then train the neural network. But we have to do that for all kinds of different parameter settings, right? So there's this training process can take quite a long time because you need, for all possible parameter values that you might see, you have to do that training.
Yeah.
How long does that take?
Okay, so let me answer this way. So one of the things to realize in this is that, okay, let me just first give this answer. The main benefit in this method is not the reduction of training time. So the initial cost, let me just go back here. The initial cost might be high. Oh, wow, what's going on here? But so even though the initial cost is high, afterwards, once you have these trained likelihoods, you can actually reuse them. And in fact, for most of the Akili project, it is only these choice probability networks that I mentioned in the very end, where we had to go through the whole training process for our project with Akili. The LANs that we used, so these the reaction time and choice networks joined, those were actually reused from me having trained them literally 1.5 years ago once on a machine that was in correspondence with a publication back then. And I was able to just reuse them. Okay, so this is just to contextualize this question a bit in terms of what one might care about a lot. But now to directly answer the question, how long it took to train those in the first place. Well, For this, we are relying on a compute cluster, or back then we relied on a compute cluster. So if you would want to directly replicate that process on a single machine, it will probably take you something like a month of simulation. But I want to emphasize that we did not actually actively minimize the number of simulations that might be necessary for training these. So we were focused mostly on the reuse aspect. Yeah, okay, that's already a pretty long answer. So if there's a follow-up question,
so training
I'll expose more details.
Training can take indeed a very long time, but of course, the scenario we are in is that we only have to do that once, and 2 days later we can use it. And then, of course, in the sampling process, we can evaluate it very quickly. We don't need to retrain. Which also
actually exactly. So I don't know if that was part of the question, but the evaluation is literally less than a millisecond.
And of course, there we're benefiting from the fact that neural networks have been optimized to death over the last couple of years. So there's a lot of very powerful technology to make that happen.
Yep.
Another question I have is for Akili, in terms of what did the analysis you did on this data look like before, and what does it allow you to do now with this new analysis method?
So before we engaged with PyMC, we really didn't have any hope of scalably even approaching drift diffusion modeling. We had done some very small forays into that, but we wanted to be able to draw some really big conclusions out of a big set of data. So that's why we kind of came to PyMC for help. And our first attempt, as Alex went into it before, our first attempt on the existing toolkit as it was just untenable. Alex slogged through iterations that took weeks to try slightly different things. And if we're going to tease out what is really happening with a different task that doesn't match exactly the standard literature, then we really need to try some things with a much greater cycle. And then if we want to be able to leverage that in production with patients in real time, or somewhat approaching real time, then we definitely need some tools that would be much more computationally efficient.
Yeah, I think to unpack that part a little bit more about the production context. So that's a use case that we're thinking about using this tool, and there the inference time is actually really important, because we need to be able to fit these. We have the model, which takes a little bit to train, which is okay. But then once we have that model, we want to be able to deliver, things like feedback to a patient quickly. So whereas other approaches may be faster at the inference step, because of the kind of class of use cases that we're looking to get into, it's really important to have speed at this inference step.
And is there more you could say about the application? Like, so you fit the model, like a kid, I guess, plays the data for a month, and then you fit it. What type of feedback?
So there's a couple use cases I can comment on, and maybe Titi can comment on as well. So there's the use case of a development tool where we leverage the model to make development decisions without having to run clinical trials, for example. So that's one potential use case for this kind of thing. But then there's other, so if we wanted to say, give feedback to a player in real time as they are progressing through their treatment. That's where we really need the ability to do this very quickly. It wouldn't suffice to make a measurement and then 2 weeks later deliver some feedback that is no longer relevant. So that's why that inference compute time is so important for that class of use cases.
Yeah, it's a very common thing for the patients or the care team to want to understand, okay, how much impact is this having? And they can observe things like symptoms or behaviors, but they can't really observe what's actually happening inside the brain. And we want to be able to uncover that and expose it for them as much as we can, and then add to our own understanding of what are the exact mechanisms within the game that are having the right impact, and tune the game accordingly.
Got it. Yeah, very interesting. So yeah, I mean, one thing, I guess, from our perspective of working with you that I found just really rewarding and interesting was that obviously you're data scientist yourself with cognitive science background, so a lot of expertise already, and like knowledge in Bayesian modeling. So that always makes it much easier for us if we're able to basically, and that is often our goal, try and act as an extension of the research team and bringing that expertise, and also try and transfer that knowledge. So I guess I'm just curious whether that was successful. Like, were you able to also instill some knowledge, and maybe how that collaboration was from your side, and how you thought it was structured?
Yeah, I think it was a very successful collaboration. I've had many consultants working with in the past, and I think this is by far the most successful collaboration that I've seen. And yeah, it was, like you said, I think we were able to quickly establish the sort of boundary of where we needed to interact on a frequent basis to sort of talk through, okay, this is where we are, from the scientific perspective and from the technical perspective, and these are some good next steps, and then iterate on a weekly or bi-weekly basis to make really significant progress. I don't know if Andy, you want to talk, since you were in a lot more of those meetings.
Yeah, I think like Titi mentioned, we've had a couple engagements now with the PyMC team, and they've all been really great. And I think what we did is typically we'd meet frequently to set up and really set clear goals for a project, make sure we're all aligned on exactly what we're trying to achieve. And then Alex, Ricardo, and I would meet bi-weekly, say, just checking in. But I really trusted them, because they always produced, I always had stuff to bring back after every meeting that we had. It was a very positive engagement. And we are in the context of a PyMC Labs webinar here, but so you might think we're just preaching here, but really no, it was awesome. I'd recommend them to anybody.
Well, thanks so much. That's obviously great to hear. Yeah, and
also,
I mean,
we can give the compliment back, to be fair, right? I think you've actually also, I mean, I could feel that you guys were quite trusting of our efforts, and that also it makes it much easier to think things through.
Yeah. And I mean, yeah, as I said at the beginning, the application domain is just really so interesting. Like, yeah, not always do we get to have such an impact, I guess. I also had another question for Alex, and maybe then we can take some questions from the audience. Is these networks and the way you present them are very much tied to the drift diffusion model. But in principle, anything that you simulate, like maybe differential equations, or maybe have some very complex industrial process, right, that you can't derive a likelihood function for, could this technique not be used for that as well? And do you see any limitations, like maybe for scale, if it comes to that?
So in principle, I would say that as like a tested scope of application, so they are definitely not tied down to in any way to these drift diffusion models per se. The drift diffusion model is just one great application, and it's close to home from the perspective of the intellectual landscape. But they can certainly be used for a wide range of applications. And only, let's say, limiting factor here would be the amount of training data you might need if you have a very high dimensional process. So if you actually have very high dimensional parameter inputs, then you might run into trouble. So there's of course there's a landscape of methods. They have varying sort of like costs and benefits, right? So there are not only LANs out there, but for LANs, I would say the main limitation would be if you have a model that has more than 15 parameters or so, I would be cautious. And that's actually sort of a limitation that LANs share with a bunch of methods in this simulation-based inference space.
But
And let me just
LANs
add that,
paired with something, sorry to interrupt, but LANs paired with like, you know, some active sampling approaches or ways to make the model fitting more efficient could help to crack that problem. So there is potential to build on top of what you've already done here.
Definitely there's potential. And I want to like just mention one thing here is that okay, two things. Sorry for the miscounting. One thing is that these kind of models that sort of, you know, why Akili cares about drift diffusion models is because they're interpretable, and you really want to sort of get insights at a level of the cognitive process out of this, right? And there is sort of in common what interpretable models in science have in common is often that the parameter input is actually not very high dimensional, right? So the scope of applications, especially for these, let's say, scientific computational modeling, sort of in the cognitive science realm or so, projects is. So for that kind of realm of applications, these things are well suited because people are explicitly want to have models that don't have too many parameters, right? There's value in that, as per, you know, you might raise your Occam's razor or whatever, right? But then also I want to mention one other thing is that it depends what one means now by parameters, because if you consider hierarchical modeling, right, across like, let's say 100 participants here, 100 gamers, right? And you want to sort of impose a common distribution, a common like high level distribution from which parameters come that then sort of is a shared set of information, right? And the respective gamers have their own sets of parameters, right? So you could consider that a very high dimensional problem, but that's actually modular. So for those kind of things, LANs are immediately applicable, right? Because you are just using the same LAN for every participant, even though your actual inference problem has like hundreds of parameters in the end. Here, it's not a bottleneck, right? That's not a problem. The problem only emerges if the single component has many parameters.
That's a great point. Yeah. So especially for hierarchical models, right? Like we are using, that is very powerful. So it really integrates nicely with the whole Bayesian modeling stack, because it's really just the last part that you approximate and also have through the code that you wrote just be packaged very nicely that it does look like a likelihood function, and you just plug it in and it just works and it's fast.
Yep, exactly.
Yeah, and just before we turn to questions, just wanted to say, you know, this work has been very impactful for, you know, towards Akili's mission. But you know, it has many the use of LANs in the PyMC stack has a lot of potential and many different use cases, as Alex was mentioning. And so we realize that, and we want to want to share that value with the community. So we do intend to open source the work that we did with Alex and Ricardo in the very near future, and we'll make an announcement about that. But we hope that there's some interest there to take it and run with it. Or even if you're just interested in getting a deeper understanding of the approach, you'll be able to see it there. So we'll make sure that gets communicated in the right channels.
Yeah, very cool. So that is always an extra bonus when the work that we do, which is obviously comes from the open source domain. And of course, PyMC Labs is a for-profit company, but then when that work can contribute back directly to the open source and make that better.
Right, we
closely
rely
aligned
on,
with our mission, and
Yeah.
amazing when clients also are aligned with that. Cool. Well, we have some questions from the audience. So Andreas asks, what other conditions besides ADHD are good candidates for this type of application?
For the Endeavor, or basically the underlying engine we call is the selective stimulus management engine. So that technology, we've run trials in major depressive disorder and multiple sclerosis, Alzheimer's. There's lots of ways in which attention is implicated in different types of diseases, even ones you may not necessarily think are primarily cognitive. There are cognitive impacts. So, it's got a lot of potential applications.
Great. And Ritesh asks, in COXA experiments, data may be quite scarce per experiment. I mean, maybe 20 subjects with 50 trials each. Is this data enough to use ABC?
we have, so in contrast to classic, psych experiments, the typical regimen is a child plays for 25 minutes a day for a month. And so that's a lot of data. And then we have volumes of subjects or patients as well. So I would say that, yeah, we do have enough data to do this in the right way.
Yeah.
I mean,
so
maybe I can just, sorry, go ahead.
Go ahead, Alex. Yeah.
Yeah, I just would add to this that specifically for this question now, in case Ritesh is interested in that use case, I would rephrase the question slightly and not necessarily ask if ABC is useful in such cases, but rather if the model one has is amenable to parameter estimation from such few data, right? It's not necessarily whether or not you use approximate Bayesian computation. It's the question is raised on the level of how much does such data, so a few data points, how much could they in general even constrain the parameter space to make inference useful? And again, to hark back, like if you have 50 trials and just one subject, it's a slightly different situation from having 20 subjects and 50 trials each, because you can apply hierarchical modeling, and that can really help you a lot, actually. If you look at the problem this way, then you can share information across the trials if you want.
Yeah, we actually did some analysis earlier on when it was just Thomas doing the work with us, where we compared hierarchical versus individual. In our case, because we had so many trials per individual, the hierarchical goal didn't give us a benefit. But in case when you have so much fewer trials, then hierarchical is a big win.
Yeah, and we leaned on some priors in that situation as well, right? So good priors can always help you in limited data situations.
Yeah. So.
And maybe also a point of clarification that the number of data points you have to fit the model or that are in an experiment are not related to the training. So the training is completely irrespective of how many data points you later want to use it on. You train it on millions, probably more, Alex would know. If it took a month to train, hundreds of millions probably. of data sets that you're generating for all kinds of different parameter combinations that then gets embedded in the neural network weights. And then you just take those weights and apply it to whatever data set you have, just like any other likelihood function you would use. So yeah, that's really such a cool benefit of this is how it integrates and literally just replaces a standard likelihood function with a new one. And that reminds me of another really interesting finding of this, unrelated to that question now, where in some formulations of the drift diffusion model, there is a closed form likelihood function. Only for the other ones we wanted to use, it was not available. And also we didn't have gradients. So this was basically two benefits of using these LANs. But even in the case where we have a closed form solution, because the drift diffusion model is quite slow to evaluate, that closed form solution is difficult to evaluate. So you can do it. And in this case, the approximated version with the neural network is still faster than the one that you write down. So it's not basically the case that, well, when you do have a closed form solution, you should always use it. Even in that case, it's actually faster sometimes, and it was in this particular case, to use the neural network one. So I thought that was just, to me, it was mind-blowing that like, oh, well, you just have a simple mathematical formula that has to be faster, right? But well, no, just some dot products, which is what a neural network does, was even faster than that. So yeah, it can have benefit even in cases where you can write down the likelihood function just because it might be slow.
I don't know to what extent you've optimized your LANs for speed of forward pass. Like that's another area of potential interest, is designing networks that are specifically meant, requirement is that they're fast. I think accuracy was probably your main metric, but it depends on what your use case is really at the end of the day.
So Rejosh asks, if I understand correctly, I can use Alex's trained neural network for drift diffusion likelihood for my use case. Exactly. So yeah, you don't need to train the model. The model is already trained. You just need the weights, which we provide. So that's an HDDM, and it's going to be in the library that Akili is going to release, and just use it. So yeah, you don't have to do a month of training unless you have your own custom model, and model here means likelihood function. So if you have a new formulation of the drift diffusion model, or of like your very custom thing that gives rise to the likelihood function, then you need to do the training. But in this case, the training was already done for you. You just need to use the likelihood function, and it's going to be fast, no training required, and you can use it on the data set. So that's how that is.
We need a library of models.
Sounds like we do, yes. So stay tuned for that and more. Which is a great point to conclude on. We're at time. That was a lot of fun, and I really enjoyed the discussion and all the questions from the audience. Thanks everyone for tuning in. It's great to see that there's so much interest in these methods and in cognitive approaches and open source. So thanks for being a part of the community. We hope to see you in other meetup events, and of course the PyMC channels, and definitely check out Akili as well. Thanks everyone.
Thank you, Thomas.
So,
Thank you.
So see ya.
All right.